Let's move to the next talk. The next one will be Professor Stephen Cummer from the Duke University, and with a really exciting talk on wavefront control with the acoustic metamaterial concept and application. Please, Stephen, when you are ready.
Thanks very much, Vincenzo. Thanks, everybody. Thanks for attending. And thanks for the invitation and opportunity to present some of my group's recent work in this space, focusing on acoustic metamaterials and wavefront control on relatively small scales, and with relatively thin metamaterials. I definitely have to acknowledge the key contributors from my group: Terry Shen, former postdoc, who's now has a faculty position at Rowan University; Junfei Li, who's a postdoc in my group; and Xiuyuan Peng, who is a PhD student in my group. Did a lot of the heavy lifting on what I'm going to present. So, you know, the metamaterial concept just continues to give more and more and more, and it remains sort of remarkable to me how widely applicable it is to all sorts of wave and transport systems. Of course, it got its start in the electromagnetic space and optic space, but it was easily adaptable to acoustic space, to elastic space, and just about any wave or more generally transport system that you can imagine. Heat transport, diffusion, all of these, all those subfields are now adapting metamaterials ideas to control fundamental transport phenomena. In the acoustic space, you know, just about any object that you can imagine that interacts significantly with acoustic waves, it can be assembled into a metamaterial structure. This, I'm just outlining some of the examples from the literature going back to the very beginning. About 15 years ago, just a scatterer array in the right orientation can create effective acoustic anisotropy. Helmholtz resonators, of course, were one of the big ones in the beginning to give negative effective bulk modulus. Perforated plates have all sorts of different effective material properties depending on the regime that you explore, whether it's deeply sub-wavelength or in the phononic crystal regime. Resonant membranes as well, elastic membranes that can strongly interact with acoustic waves. Something as ordinary seeming as soda cans can do a pretty good job, and something as carefully engineered as porous silicone microbeads in a gel substrate can be used to control acoustic waves and transport by exploiting the interaction with that engineered structure. Bubble suspension in an elastic substrate, and in air, hard structures that control the acoustic propagation and lengthen its effective propagation distance in relatively small structures using the idea of coiled space or labyrinthine structures. All of these building blocks are great for acoustic metamaterials, depending on precisely what you want to do. Of course, one of the challenges in all of metamaterials that those of us in this space are fighting all the time are losses and the ability to fabricate very large structures with precisely controlled interior structure. I feel like in 10 years, fabrication technology is going to be in a place where we can really finally create metamaterial structures, volumetric 3D metamaterial structures that span many tens of, or even hundreds of wavelengths on a side and have precisely controllable inhomogeneous structure in the interior. But we're really not quite there yet. And so both the RF in particular and acoustic metamaterials communities have pivoted pretty hard to figuring out what can we do with thin acoustic metamaterial structures or acoustic metasurfaces that are generally sub-wavelength in overall thickness, which makes them a whole lot easier to fabricate and to experiment with. And what are the limits of what you can do with those small structures? So sort of broadly, the idea of a metasurface is controlling the relationship between an input wavefront and an output wavefront. It's wavefront transformation in a sense. Good examples from the literature, again, are the resonant membrane metasurface on the bottom left here that can be used to create very effective acoustic absorption in a relatively thin layer. Also, transmissive or reflective metasurfaces that are not designed to absorb, but are more designed to transform one incident wavefront into another on the transmit or receive side. One example of this kind of thin metasurface is an acoustic lens, for example, that's transforming a spherically expanding wavefront to a spherically converging wavefront. And what kinds of unit cells can work with that? Labyrinthine, where you control phase, is a very good one. And as an example of something that we did some time ago now, I'm going to go very quickly through this one to highlight some of the ideas, is an acoustic hologram. If you want to project a complicated sound field in order to create a particular shape of an acoustic sound field, that can absolutely be done actively with an array of sources, where you have the ability to control amplitude and phase of each one of those and tune it. And this is actually done in all sorts of acoustic applications on small scales and large scales. The complexity, of course, of running so many active sources is not trivial. And so we just asked ourselves, what if can we use passive metamaterial structure in order to project a relatively complex spatial acoustic hologram from a single source that produces a relatively simple wavefront? And phase control is by far the easiest way to try to do this in an acoustic metamaterial. And so our building block for this effort, which was published by a former PhD student in my group back in 2016, is that labyrinthine unit cell. And if you look at the image of what was fabricated here, you can see that each one of these unit cells is a little bit different, and it has different degrees of space coiling within it in order to create larger phase delay, for example, in the cells that are more coiled, and less total phase change in the unit cells that are less coiled. For this acoustic hologram exercise, we did create 13 different labyrinthine unit cells to control transmission phase with 15-degree steps. And the cells were designed and optimized to have relatively high amplitude transmission, at least 75% for all of the individual designs. And of course, 3D printing is sort of the enabling technology for this sort of thing. I mean, the exercise of fabricating a lot of unit cells like this without 3D printing would be tough, but it's actually quite easy with modern 3D printing. And so the hologram that emerges is a 2D acoustic metamaterial structure that looks something like this, where every one of those unit cells is transmitting a slightly different phase in order to project the sound field that we want. In terms of spatial structure, the goal was to project the letter A, first initial of the first author, Abel. And this was done in collaboration with Yoon Jing at North Carolina State, although he's now moved to Penn State in the acoustics program there. Did this experiment in an anechoic chamber, speaker radiating a known wavefront through this hologram and scanning the sound field, the spatial structure in the image plane here. The expectation and measurement. Hopefully you'll give me a little bit of wiggle room here and let me declare that this is in fact the letter A. If we were doing this again, for sure, I think we could do a better job, but I think it illustrates the idea of using these phase control elements to control wavefronts in acoustics. There are limits, though, to the kind of wavefront control that you can do when you control only phase, which is by far the most commonly used approach in both electromagnetics and optics and acoustics, because one space where that the limitations of phase control emerges if you look at what happens when you're trying to do something as simple as bend the angle of incidence or the angle of transmission of an incoming beam, that if all you can do is control the local transmission phase, you get all kinds of additional diffracted modes through a system like this that you do not want. And so in collaboration with Sergei Trechikov and Anna Diaz-Rubio at Aalto University in Finland, we started to ask ourselves, can we do better and what would it take to do better? This is work that was published again now a few years ago in 2018. But what does it take if we want to come up with a metamaterial structure that can simply transform one incident wavefront, relatively arbitrary, into a transmitted or reflected wavefront that's completely different without any unwanted diffracted modes? And as an example of how this design process works, illustrating this with a couple of plane waves on the incident side and the transmitted side with no reflected wave. And so we're able to actually write down the complete acoustic fields on both sides of this as yet unspecified acoustic metamaterial structure. And if we assume that the limitation in terms of conversion has really nothing to do with amplitude per se, it's all about conservation of normal power flow normal to the interface on both sides. And depending on the angle of transmission relative to the angle of incidence, that can yield a amplitude of transmission that is larger than 1. And that's okay, because that can still respect power conservation. But that presents a problem when you're using, for example, phase control acoustic metasurface elements that by design, you can get a transmission coefficient of 1, but you cannot get one that is larger than 1. So taking a step back from this notion of amplitude and phase control, it turns out that really the right way to formulate this problem is in terms of surface impedances, where we can fully write down the total fields on the incident side and the total fields on the transmission side and derive what the required surface impedance is for this acoustic metasurface on both sides of the interface. And the interesting thing that emerges, and this was what Trechikov and Anna Diaz-Rubio reported back in their 2017 paper for electromagnetics, is that key feature is that the diagonal elements are not equal to each other, which means that this metasurface has to have an intrinsically asymmetric response, which is the acoustic analog of bianisotropy or Willis coupling in the elastic literature. So given that, for a particular wavefront transformation, it is easy to write down the spatially varying elements of that impedance matrix and plotting them as a function of position, transverse position across the interface. If it's plane wave to plane wave, then there is a periodicity that emerges in the overall material parameters. And we can then extract from that impedance matrix, we can extract what the local transmission and reflection coefficients have to be for such a structure in order to move towards making this. And of course, what we see is a local transmission coefficient that sometimes can be larger than 1, and reflection coefficients from the 2 different sides that are not equal to each other because of this phase factor. So that again is the reflection of the asymmetry or effective acoustic bianisotropy that must be present in the system. So how to control that asymmetry and deliver unit cells that match the required transmission and reflection coefficient on both sides. We found empirically that transmissive unit cells with 4 individual Helmholtz resonators are sufficient to make this work reasonably well. Any fewer than 4, and you have to run the system quite close the operating frequency has to be quite close to the resonant frequency of at least one of those resonators, and it gets very lossy. With 4, you have the ability to move the operating frequency away from those resonant frequencies, and so have relatively high efficiency. So this is just your standard metamaterial unit design, where we're coming up with a range of structures that deliver those local transmission and reflection coefficients that map to the required surface impedance on both sides. And in simulation, this is sort of how we expect things to go. Let me just highlight this middle one, for example, where we have an normally incident plane wave, and we are trying to transmit to a very steep angle of transmission of 70 degrees. If you try and do that with a phase-only metamaterial, you can see there's all kinds of additional modes here, both on the transmission and on the incident side from unwanted reflections. And the overall efficiency of transformation of that normally incident energy is below 60%. But by targeting the surface impedance on both sides using this approach and exploiting that required asymmetry in the system, you can get a vastly more efficient transfer of energy from your incident mode to the transmit mode. And sure enough, this works pretty well in experiment as well, where we are transmitting a normally incident Gaussian beam to 60 degrees, experimentally measured sound field versus simulation. And you can see the relative purity of that transmitted wave without very much reflection and without very much many unwanted modes on the transmit side. And experimentally, we can show that 97% of that transmitted energy goes into that desired mode, whereas if we were doing this with another approach, it simply would not work. All right, so pivoting to a slightly different topic, and let me motivate why we did this. You know, airborne acoustics, there's a lot of concepts that you can demonstrate there, but the structures tend to be pretty large. Losses are really challenging to manage. And in terms of developing concepts, it's a great platform for demonstrating concepts, but pivoting towards applications, finding something that might actually work in practice is a little bit challenging. So in the last couple of years, we have been thinking a little bit more deeply on smaller spatial scales and in water. And in one of those spaces, a key application is acoustic tweezers, using acoustic energy to create forces in water for contactless particle manipulation. And there are a bunch of very good people working in this space, Bruce Drinkwater, for example, and I am lucky to have Tony Wong in Duke University's mechanical engineering department. So we started talking with him about kinds of things we can do and adapting metamaterial ideas. And I'm going to show just a couple of examples fairly quickly of our most recent work in the space. The overwhelming majority of acoustic tweezer demonstrations use radiation forces from the acoustic waves in order to push and trap particles, where the particles are moving to pressure minima and maxima in a standing wave pattern. One really widely used platform for this, it uses surface acoustic waves and generates a two-dimensional standing wave pattern by putting an array of IDTs, interdigitated transducers, that launch surface waves onto a piezoelectric material, and you can create a standing wave pattern in above that piezoelectric material that then has the ability to trap and move particles around in 2 dimensions. One limitation of this approach is that using standing waves like this, you tend to create a lot of stable trapping points and don't have a lot of spatial selectivity. And it does require a lot of transducers around the edge of the domain where you want to trap particles. There have been some demonstrations of 3D trapping that again use an array of transducers that can trap and hold individual particles. the requirement of having a lot of transducers that need to be controlled is a bit limiting, and the vertical forces in such a trapping configuration are quite small, and so there's a very limited range of materials and particle sizes and masses that can actually be trapped. Now, there is another force in these acoustic systems underwater that can be exploited when the power gets higher, and that's streaming. I've got a looping video here, and I have no idea whether somebody can, everyone can actually see the motion here, but we have an acoustic transducer underwater. And if you look closely, you can see small particles that are being driven upward quite fast by this acoustic energy. And so this is work in collaboration with David Fan from NTU in Singapore. And the idea is, can we use streaming forces in that third dimension in order to create a stable 3D trap using one single acoustic transducer? And the idea here is a streaming acoustic vortex where we create horizontal trapping in the two transverse dimensions using the radiation forces. So what we're doing is creating that vortex field that has a stable trapping point along the axis of the vortex field. And then the vertical trapping in this dimension is taken care of by fighting gravity with streaming forces instead of radiation forces. And how, an illustration of why we need to use streaming for that three-dimensional trapping is in a conventional acoustic vortex, the in-plane trapping forces, where those are largest in the center of that focused acoustic vortex, moving down to the same position, that is far away from where the strongest radiation forces are in the vertical direction, unfortunately. And so we need extra forces in that point. And actually, let me go back then to illustrate what this, the acoustic vortex lens that we created and designed and created out of PDMS that just goes right on top of the transducer in order to create that phase distribution that yields the acoustic vortex a handful of wavelengths away. So the design went amazingly smoothly. First sample actually worked, and set up the experiment to show that when we have that acoustic vortex lens on top of a transducer, particle imaging velocimetry shows very clearly that we get strong streaming. And as a demonstration of the trapping, even if you can't resolve the video here, hopefully you can see that there is this red particle that is being suspended above the transducer with that acoustic vortex lens. Streaming is a little bit trickier to control than radiation forces, which is why we get a little bit of dancing around of that particle, but it is absolutely stably trapped in the system. And so you get a lot more levitation force, and can therefore trap a much wider range of particles than you can with other approaches. And this is all enabled by careful acoustic wavefront control. One last topic that I'm going to mention, because I think I have 5 minutes left, and this is also relatively new work in that acoustic tweezing and surface acoustic wave space. Again, those 2D standing wave acoustic tweezers have been super successful for a lot of potential applications. And you can make them a little bit dynamic by tuning the phase and the frequency of these different source IDTs in order to move the acoustic standing wave pattern around and translate some of these particles. But there are some limitations on the complexity of the dynamics and the overall shape of the sound field that you can project in the space when all you have is control over acoustic sources on the edge. And the metamaterial way of thinking about this, one would imagine, boy, wouldn't it be great if we could somehow locally control those surface acoustic wave fields in the vicinity of the actual trapping locations. And we would get a lot more spatial precision, and we could do quite a bit more, I think, with that ability. So how can one do that? This is a first step towards that goal. The idea that we came up with is to control the electric conductivity of a surface layer on top of that piezoelectric lithium niobate substrate. And it's actually well known that if you control the conductivity of a thin surface layer on a piezoelectric in which surface acoustic waves are propagating, because that material is piezoelectric, there is a feedback between the elastic and electrical properties, and the presence of a conductive layer or absence does influence the propagation of those surface acoustic waves. And that's something that's used in a number of sensing applications, especially gas sensors in very harsh environments where a surface is activated with a polymer whose conductivity changes when particular gases are adsorbed. So our question was, can we develop a controllable device to actually modulate the conductivity, electric conductivity on a thin layer on top of a lithium niobate substrate? And our first solution that worked reasonably well was a carbon nanotube thin film transistor. Semiconductors, obviously a very natural approach to do this because you can modulate electric conductivity via carrier injection. But one challenge is that you don't want to stick something that's fairly massive on top of that substrate, because then the mass loading undoes the control of the surface acoustic wave that you'd like. So carbon nanotube fiber is ideal for that because it is relatively low mass and does not really influence the mechanical aspects of the saw. We actually have the ability to tune that conductivity with a relatively low gate voltage on the order of a volt instead of tens to hundreds required by other approaches. But we also need to make sure that the gate electrode that we're applying this voltage control that influences the conductivity is at least a handful of microns above that substrate, because otherwise we're putting conductors right next to the piezoelectric, and we lose the ability to control because that conductor is already there. Crystalline nanocellulose turns out to be a great gate dielectric to do that, to create that standoff distance, again, because of its electric transport properties and also its low mass. And this is work that is just now in press, a collaboration between myself, Tony Wong in mechanical engineering here, and Aaron Franklin, who's the fab expert and the CNT and CNC expert in my department in electrical engineering. Oops. And the overall structure that was fabricated and tested looks something like this. Here's the macro view where there's an IDT on this lithium niobate substrate launching surface acoustic waves going in this direction. There's another IDT on the other side not shown. And here's that thin film transistor made out of carbon nanotubes down the middle. And the crystalline nanocellulose gate dielectric. Maybe it's a little easier to see in this cross-sectional view of the device. Also with silver nanowires as the gate electrode, because it's not so easy to deposit solid conducting layers on top of something fibrous like crystalline nanocellulose. But this turns out to work perfectly. And so by changing the voltage on this electrode, we change the conductivity of the carbon nanotubes, and the surface acoustic wave traveling across that has its velocity modulated. The experimental device shown here, where the IDTs are a little bit tricky to see because they're small here and here, and the thin film transistor here, and great agreement between the predicted velocity change and the measured velocity change, and decent agreement on the modest attenuation changes that also come in that sweep of conductivity. 2.5% of velocity control doesn't sound like a lot, but this really is 4 times better than has been previously reported, with 30 times less voltage applied to the controlling device. So there's plenty of more work here, but you know, borrowing metamaterials ideas for surface acoustic waves, I think it does open the possibility of local control of those saw fields to improve acoustic tweezers and other applications that rely on surface acoustic waves. So last thing, parting thoughts. Those ideas that emerge from acoustic metasurfaces, I think are themselves a really powerful approach for controlling acoustic wavefronts and fields. But even just having some understanding of the approaches that work in the acoustic metasurfaces space gives you the tools to adapt those ideas and map them onto more application-oriented domains that are not, strictly speaking, acoustic metasurfaces, but absolutely borrow the ideas from that space. For sure, there are remaining some interesting fabrication challenges. I feel like that's the limiting factor in the field right now, is the complexity and size of devices that we can make. But that hierarchical metamaterials and metasurface design approach, where we can focus our design effort on individual unit cells, and then the bulk properties that emerge from that are relatively easy to understand in terms of that local control. You know, that's the whole power of metamaterials and metasurfaces, and I think will continue to yield lots of interesting potential applications. Thank you very much.
Thank you to you. Really impressive talk and results. I have at least one question, because when I have a question about the acoustic tweezer, let's say.
Okay.
I mean, if I understand well, I mean, it's not so you were saying that it's not so simple to, I mean, have a kind of standing wave pattern, and that was mainly the idea why you went on the other configuration where you try to trap a single particle. And now that configuration works really as tweezer. I mean, let's suppose that you move your, can you move it first? And the top of the surface of the liquid doesn't matter, is important?
Okay, great questions, both of those. So the upper surface doesn't really matter in this. Of course, that upper surface, that free boundary between water and presumably air, is highly reflective. So we need to make sure where we're trapping is not too close to that, so that the acoustic vortex fields, which are spreading out, but they don't reflect back and influence the field that we're trying to create. And can we move it? Absolutely. But horizontally, if we need to physically translate the transducer in order to move
of course. But okay, I mean, it's not deviating. I mean, it's trapped. Yeah.
Right. And actually, I'll mention part of the motivation for this was the application idea of silicon wafer cleaning by trapping a bubble and being able to sort of scrape it across the surface of a fabricated silicon wafer with, you know, no brushes, no aggressive contact, but just something, a bubble that you can push around to make that surface.
Definitely a good idea. Yeah. This implementation, are acoustic metasurfaces power limited somehow?
You know, it very much depends on the wave domain and the approach used to fabricate them. In terms of airborne with solid structures, I mean, I would say no, unless the coupling to the solid structure becomes so large that you start to physically damage your structure. In water, sometimes you know, there are much stronger nonlinear effects that emerge in water as you increase the power. So that's something that both limits the applicability, but if accounted for correctly, also can be exploited.
Okay. Then the other question is, can we use, I just lost, yeah, can we use, could we imagine using the trapped particle as motion sensor?
Yes, sure. I think that would depend on the details of the application. But yeah, I mean, that's a great way of thinking about it. So much metamaterials work is let's demonstrate something we can do that's hard to do by other means, and then let's figure out what to do with it. So it's a great idea.
Yes. Okay. Thank you.